Okay, so one more day after this of chapter 16, and then review, then exam. So we have a hanging spring here. This is kind of review. If I made, what's the mathematical symbol that describes the parameter of that spring, the stiffness of that spring?
Okay.
Big, yeah, K, small k. So if K was, if I made K larger of this spring, what would happen to its frequency? If I made K larger, the frequency stays the same?
Doesn't it?
It increase? The math tells you, right? The math tells you. Because K, make K bigger. Make K bigger. Come on. Make K bigger.
Oh, okay.
Now, this isn't the symbol for frequency. What was the symbol for frequency? Well, this is, what do we call omega? Angular frequency, right? Frequency was nu, and that, or F. Do you remember what it was? I think I just told you, Mel, like 10 minutes ago. Isn't it 2 pi f or 2 pi nu?
Oh, yeah.
All right, E is omega. So I increase K, yeah, frequency will increase. Okay. What if I put a smaller mass on there? What will happen to the frequency? No, I didn't change the K.
Oh.
So all I did is I popped off one mass and put a lighter mass on there. The math says what's going to happen.
Because then the bottom's getting bigger.
This is a smaller mass.
Oh, when does it say increase?
Is that what you said, increase?
Yeah. You said increase at first, yeah.
Yeah.
I thought it got bigger.
Okay, so, and it looks weird, I think, because they have a little mu down here, not an M. An M makes sense when you have how many objects moving? One. When you have one object moving, you use M. So pretty much in all of general physics has been M. But now we're going to be talking about section 16.9, molecular vibrations. Well, is there one little atom moving in a vibration? That's not possible, right? You got to have two things moving at least, otherwise you're not going to have a vibration. So now, all of a sudden, you don't have M anymore. You have reduced mass. And that's pretty much, this is just for the atoms that are moving. That's what's involved in calculating that reduced mass. All you care about is what's moving. But you're right. If I make the mass smaller, right, I'll be dividing by a smaller number. I get a bigger number. Maybe taking square root, but still, I'm getting a bigger number, so the frequency will increase. Yeah. What can I do to this system and the frequency will not change?
Pull it harder.
Pull it harder, right? Yeah. Frequency won't change. Pull it even weaker. Frequency won't change, right? That's just that's going up the energy ladder, right? The vibrational energy ladder. It's hard to imagine because we can pull it down any distance we want, but we can apply whatever amplitude we want. But okay. If we were gonna play around with this, I'm sure you will in the homework. What was new with the tilde again?
Wave number.
Wave number. Okay, so if you're gonna use this expression to get angular frequency, what units the little c need to be in?
Centimeters per second.
Speed of light in centimeters per second, exactly. All right, otherwise this is gonna be messed up. Okay. Can you read this axis, Mal?
Potential energy.
Potential energy. Good. How about this axis, Jeffrey?
Displacement.
Displacement. What's displacement? Alyssa, what's displacement? We can talk about this vibrating spring system. What's displacement?
It's like, what does that have to do with energy, right?
Yeah, you change displacement, you have a different potential energy. It matches this motion pretty good. Anybody help her? What's displacement?
The position of the mass relative to the equilibrium point.
Subtracting, right. And it's given a direction. That displacement's a vector. So either it's, let's see, where's the equilibrium point? Right there, right? So if I pull it down that distance, it's down, so it's negative x, and it's whatever centimeters that was, or meters, right? If I go up here, right, then it's positive x, so many centimeters. So that's displacement. So that's what that x-axis is that little, that's the vibration, right? You have one atom up here and one atom down there at the bottom of that spring. And then I wish they would have, but they didn't. They should have put their little energy ladder in here, right? Depending on which, I guess, you're talking about. I could change colors here, maybe make them green. So the other guys are green. Oh, whatever. But you know what I mean? There's those energies levels, vibrational energy levels. So as I increase the what, I'm jumping up this. Let's just stick to the blue guys. What's increasing as I go up here in the motion of that vibration? Is the frequency changing? The frequency's not changing. What's changing? Amplitude's changing, right? So it's just getting higher and higher amplitude, right? So sooner or later, Jeffrey, I would figure what's going to happen if I get, right? What's going to happen if I just keep increasing this amplitude?
You're going to mess up the spring?
Yeah, mess it up or bust the system, right? The idea is dissociation, right? You're going to break the bond. But you're right, in this world I'd mess up the spring. But you break the bond. Okay. According to this model, can we ever break the bond with this system we have here? In other words, what are these shapes? It starts with the P. They're parabolas. Do they keep going on forever and ever and ever? Yeah. So we should keep them going on forever and ever and ever. All right. So that means, is the bond ever going to break? No, can't. Right? So where does this come from? If you remember, work is really what times what? Force times distance, FD. It's really a dot product, but we really don't care about that. Force times distance. Okay. If I'm going to stretch a spring a distance x, so my distance is going to be x, what's the force I have to use? This is going back to whatever concept preview. If I'm going to stretch a spring, I have to apply the force. Do you remember what it was? K times x. K times x. So the force is kx. See how they get their x squared? Kx squared. So the work or the potential energy is just kx squared. So that's why we're plotting out a parabola. It's just our spring system with a spring constant k. You know, and I already mentioned to you this. I mean, this is what we're going to use for vibrations of what types of molecules, if you followed what I was talking about before, right? In our angular frequency expression for these molecular vibrations, there's a mu, and now they're saying mu is equal to this expression. Well, how many atoms are involved? Two. So in these vibrations, if we're going to use these equations and use that for reduced mass, we can only have 2 atoms moving in the vibration. So we're pretty much stuck with what type of molecules? Diatomics. Right? So we're really talking about diatomic molecules vibrating. If we want to do all the math and all that stuff, that's what we're set up and good for right now. And then there's the U-do. Okay, so vibrational terms. What's the energies of these vibrational states? And it's expressed in wave numbers, not in joules. It's expressed in wave numbers. Okay. The big hint, I think, is here's a wave number out there, symbol, and then V is just a what? Is that the same V we had before? Do you remember, where did we see this V? We wrote V equals something, V equals something, V equals something, and all these different vibrational energy levels. Do you remember that?
Potential energy.
It's our quantum number. It's our quantum number for this potential energy well for vibrational energy levels. Do you remember what the lowest number it could be?
Oh, 1.
That's for a particle in a box.
Oh,
And they
yeah.
use little n.
Yeah, 0 can be.
0, 0. Okay. Do you remember why V equals 0 isn't at the very bottom of the well? Why isn't V equals 0 at the very bottom? We had some terminology. It's kind of it's a hard thing to come up with on your own. Either you remember the terminology or you don't. One reason you could say Heisenberg uncertainty principle, because if you were at the bottom of the energy well, you know exactly what the energy is. Now there's no uncertainty in the other term, and it messes everything up, so you can't really know that. The other reason, which you might have been able to guess if you remembered, is 0 point energy, 0 point energy. You can never have 0 energy. There's always, even for a particle in a box, our first energy level wasn't at the very bottom of the well. It was always up a little bit higher. So you can never reach the very bottom, okay, of that energy well. So that's our quantum number, V. Selection rules. So kind of rehashing a little bit. If something is infrared active, what has to be going on again? Alyssa, what has to be going on?
An oscillating dipole.
Fantastic. An oscillating dipole. You have an oscillating dipole, it's infrared active. Then Mel, infrared inactive would probably mean there is no oscillating dipole. Yeah, exactly. Okay. Fundamental transition is probably from V equals what to V equals what, Jeffrey?
V equals 0 to V equals 1.
Exactly. From the ground state to the first excited state is the fundamental transition. Okay. So we have a problem, though. We can't bust our bond with that type of depiction of the energy well. So let's use a different energy well to describe the motion of this vibration, the Morse potential energy. The fancy word for this is anharmonic. You get rid of the an, harmonic motion, well, that's this. That's that kind of well. So anharmonic. Now, because before, think of it this way, the harder I pull down, right, the further it goes, because F equals kx. It makes sense. That's harmonic. But if I pull it down even further, and it gets easier, that's anharmonic. It's not directly proportional. And that has to happen at some point. If I pull it down so far and it gets easier, yeah, because the bond's going to break. After it gets so far apart, that bond has to break. There isn't a bond anymore. There's no interaction. So that's anharmonic motion, and that's the Morse potential energy well. Okay. But doesn't it still look like a what down here? What geometric shape?
Parabola.
Still looks like a parabola, which is good because then all this stuff we've talked about works. And we don't have to have any fancy fudge factors or anything as long as we're sticking to like the fundamental transition. We're sticking to the bottom of the well, and we should be okay. But, you know, as you go further up, and you want to describe things, well, then things really become anharmonic, and we have to start introducing some fudge factors here. But here's some symbols here. We've got DO versus DE. Now, the anharmonicity constant is this funky looking XE. It's not really an X. I think it's a chi or something. But let's call it XE. What do you think this symbol is?
Is it the same wave number?
That's the wave number of the transition. The wave number of the transition. Where we're going from V equals something to V equals something. Hey, what's the wave number? You know, where do you see on the IR? What's the absorbed wave number? What's the energy? That's what that is. So we can get the anharmonicity constant like this, that expression. What's the difference between DE and DO? For example, let's ask you this one. The bond dissociation energy is DO or DE. The only hint you have is this plot, figure 1636. What's the bond dissociation energy? Which one would you guess? DE? Everybody agree? Mal, you agree? Peer pressure here, man. 2 out of 3. So the bond dissociation energy must be the energy that you need to apply for what to happen? To dissociate, to break the bond. Okay. To me, that energy can't be DE because I can never get to the bottom of the well. Right? Because that's 0-point energy. So DE is too big. It's just how deep the well is, the depth of the well. It really doesn't mean anything. What means something is that DO, because that's the energy that you have to apply, correct? Because you can't get any lower than the ground state. That's at V equals 0, and that's where DO starts according to this plot. So the bond dissociation energy is the depth of the well minus 1/2 wave number. Here's some what do they call that? That's like when V is changing by more than one increment, they call it overtones. I don't know if that's going to be in the homework or not. Probably not. But that's overtones. Okay. So remember, G is these vibrational terms, the energies. So that's what these are too. These are wave numbers and they're energies. The terms of those different transitions. Okay. Let's see if you see how to use it. What if I go from, let's do the fundamental transition, from V equals 0 to V equals 1. Would you be using the top? Would you be using the top term to get that wave number, or the bottom expression? You would use the top one. Okay, we're there so far. Now the question is, which V do you use? Do you use V equals 0? Or do you use V equals 1 if you want to get these answers?
Is V equals 0? Oh, V equals 1. Then it's V plus 1.
So in that expression, you should use which one?
So 0.
Which one? You see what they're trying to say? You have to go from, use this expression for v to v plus 1. So v would have to be 0 to make this work, right? You have to go from 0 to 0 plus 1, so 0 to 1. So in that case, v would be 0. So for the transition v equals 3 to 4, you use 3 in the expression. You always use the lower v. Okay, so not the higher one. Same with the bottom expression.
Let's say delta G, subscript V plus 1/2.
Yeah.
So 1 or is it?
No, it's plus
Okay.
plus 1/2. I'm just copying the notation in the book. I'm not sure why it says 1/2. Oh, that's interesting. See what you're saying? I have to look that up. So they call them overtones when your transition's bigger than 1 unit. Okay. Our Berge-Sponer, I'm not going to worry about that kind of stuff. Vibration rotation spectra. Okay. They call it band spectra. I've heard molecular spectra too. If you hear this kind of talk, and then they're talking about. And when they kind of made a jump here. They made a jump of we talked about, right, V equal all these different vibrational energy levels. Well, each vibrational energy level has one of these. If you just got to zoom up, you just have to zoom. Really zoom. And then you're going to see a little angel wing thing going on here. Because this is the rotational energy levels. Each set of vibrational energy levels, these guys, has their own complete band of rotational spectra. There's a lot of structure there that you can take a look at. And the reason why I think this is on its side, this plot is on its side, is to get across a point. I don't know if I did it or if the book did it, but the point is we like to think of transitions this way, right? Oh, we're starting here and we're going up to this one, right? But this is what you actually see on an instrument. And if you just take that absorbance spectra, any absorbance spectra, and just lay it on its side, what you actually see is energy going this way. The exact same plot. You see the exact same thing. You see energy, but then what's kind of interesting is the farther out it goes, oh man, that's population. There's more of it. So you don't see that kind of information here. There's no population information. But if you take an absorbance spectra, flip it on its side, and then you have the energy levels. And it's really easy to see with this type of rotational spectra. And then they just say, okay, you have P branch, Q branch, R branch, and all that is just what's the change in the J quantum number. If it changed by a -1, they call it the P branch. If it changed by a +1, the R branch. If it doesn't change at all, you have a Q branch. But I think that only happens for, I think you have to have a weird, yeah. It doesn't work for diatomics. You need a bending vibration. That's probably too detailed for you to even care about, but if this isn't there, you're not going to see it. I don't know what, we're not going to worry about combination difference either. And I think I only wrote down the equation for the R branch, how to calculate the wave numbers. Okay. And that's for transitions J to, yeah, because that's delta J has to be +1. I think that makes sense. So ready to do some homework? An object of mass, right? Ready to do some homework? An object of mass 1 kilogram suspended from the end of a rubber band has a vibrational frequency of 2 hertz. Calculate the force constant of the rubber band. I think we've done this kind of thing before. What expression are we going to use to get that? Let's just start here. What's the symbol?
Okay.
They're asking for K. What expression are you going to use to get it?
So omega square root of K over mu.
Yeah. Exactly. There's really no mu to calculate. That's nice.
So just use the
Use the 1 kilogram. And then they have 2 hertz. What symbol is this?
omega. Oh no, it's F.
That's,
Two.
yeah, F, or if you like to draw this guy. Right? So omega, just so you remember, omega is equal to really what?
2 pi v. Or mu.
Yeah, or the 2 pi f. So all you do is solve for K, right? Everything's even in the right units. You okay with that one? Jeff, are you good? Okay, let's go on to this one. Now we need some space. Calculate the percent difference in the fundamental vibration wave number. Okay, so they give us 2 molecules. Well, 2 vibrations, right? All they're doing is just changing the masses of them, really. Because remember, if they give you those isotopes, we just look up the U's, and we can convert them into kilograms. It's really no big deal. So what we're supposed to do is calculate percent difference in the fundamental vibration wave number. What's the symbol for wave number? Nu with a tilde. Yeah, so Enya. And let's give that one up. I'm just giving that one a prime. Okay, because the math is, if you take out all these constants, life is a lot easier. And the reason why I'm doing this is because here's the wave number and wave number prime. So wave number prime is that of the isotope with chlorine 37. How do you write an expression for percent difference? Percent difference of anything. How do you write an expression for that? Difference means what? Subtraction. So let's subtract them.
Absolute value of that.
Yeah, I would do absolute value too. Then you don't have to worry about this. Then we all agree, right? Divided by,
The average.
yeah, usually, right? And that's where things get confusing, I think. Is which one are you dividing? Percent difference with respect to which one, right? Well, for me to get the right answers in the back of the book, let's make sure we put the right one in the denominator. Yeah, I did the non-prime one, but which one's the non-prime one? The chlorine 35. That, okay, good, we wrote it up right. Okay, and it said percent, so we should multiply by 100. Okay. So, calculate the percent difference. So we just got to put numbers in for all this stuff. But all they gave you were the isotopes. So that means, what are some expressions? I had to start there. What's the expression for wave number we can use? And actually calculate a wave number, maybe. We don't have very many choices.
The 2 pi v c.
I think so. All right. If you go, that wave number would be what? Omega all over 2 pi c. And what's omega?
Angular frequency.
Yeah, angular frequency, but what's the expression for it?
2 pi f.
2 pi f, yeah, but that won't help us. And the reason why I want to go further is because they're giving us a hint. They're saying force constants are the same. That's what symbol?
K.
K. So we have to get an expression with K's in it, so we can probably get them to cancel out or something, right? So So our wave number is omega over 2 pi c, which is,
Oh, the square root of k over.
yeah, square root of k over mu all over 2 pi c. So this is what we got to plug in for our wave number. Square root of k over mu over 2 pi c. Square root of k all over mu 2 pi c. Now that's the guy without primes, right? Absolute value of this stuff. Minus, now you put the guy with primes in it. Square root k over mu. Do I put a prime on either the k or the mu?
On the mu.
On the mu, because that'll be different. Better put one there. They said the k's are all the same, so don't put a prime on the k. Do we put a prime on it in the 2 pi or the c? No, it's all the same. Absolute value. All over square root of k all over mu over 2 pi c times 100. Okay. Let's cancel some stuff out and make our life a lot easier. What can you cancel out? Top and bottom.
The whole first one.
Oh, no, never mind. Oh, yeah.
There's a bit of
Huh? The 2 pi c will go away.
Oh, we could. I can see what Al's saying. We could cancel this whole thing out, but we'd have to expand it out. We'd have to expand it out to this over this minus that one over that one. So that makes, I don't know if that's going to help a whole lot. What can we literally just start crossing stuff out? What could we cross out? 2 pi c, definitely. Is there anything else?
Square root symbol? You ever-
Not, I don't know if you can completely. But if I had,
Separate the
think if I had, instead of a k, think of it as, because it's the same everywhere, think of it as a 6. I have the square root of 6 and all that. I don't know what the square root of 6 is, but I could figure it out, pull it out of the square root, then I'd have that number in front of the square root on all of those. Then I would just cross them all out. So that means I can cross out what? The k's. And now I've got something a lot easier to work with. All I am finding now is the absolute value of the square root of 1 over mu minus square root of 1 over mu prime all over the square root of 1 over mu, absolute value, times 100. So all we got to do is find the mu's. Right? So what I would do is I would find the u's of the mu's. Right? Find those, the mass in terms of u of the chlorine and the other the sodium isotopes. Calculate the mu's. And then you're going to be left with, if each one has a u here, you're going to be left with a number, whatever it is, with what unit? U. Not u squared or anything else, just u. And then you do that conversion, right? U to kilograms. Or maybe you don't even need to. You wouldn't even need to, would you? Yeah, they're going to cancel out. Just leave it in u. That would be a lot easier. Yeah, why do all that? Just leave it in u's. Okay. So you have a, see what to do for that one? The wave number is 564.9. So I think the confusion in all this is just knowing what symbol to attach to what measurement. So what mathematical symbol is that? 564.9 wave numbers? That's mu?
No, mu with the tilde.
Yeah. Oh, new. Yeah, new with a tilde. Yes. New with a tilde. Yes. And then force constant is what symbol? K. So we'll just find K. All right. Hey, when they give you this, well, it's hard to see that that's a diatomic molecule, but it is because it has a little 2 subscript. And you know the isotopes. So that really means you can calculate what? Mu. Get. Can. Right? You can get that. So I don't think that's bad, right? How about this one? Because I'm trying to, it's always been like that, Mel. You've never noticed this?
Yeah.
Because I care. They're building from one concept to the other. They're kind of grouped. Instead of just, okay, the hydrogen halides had the fundamental vibration wave numbers. Okay, so calculate the force constants. Oh, so this is HF. That one's HCl. HBr. Oh my goodness. Okay, so they're after what symbol?
K.
They're after K. Isn't this just like we just did?
Is it just the K for each one?
Yeah.
I mean, all the K's for each
It's pretty much just doing number 11 again, right?
one.
But doing it 4 times or whatever. Right? See, what did I say? I what? I care.
Perfect.
All right, man, this is getting easy.
Charles actively.
How about this one? Nothing to calculate in this one. Which of the following molecules may show infrared absorption spectra? Do not circle which one?
H2.
Yeah. And you're done. Right? How about 22? For oxygen, delta G values for these transitions are respectively. Calculate calculate the wave number and XE. Assume YE to be 0, whatever the heck that is. Okay. How many things do they want you to calculate?
2.
There's 2 unknowns. So you better work really hard at getting how many equations?
3.
Well, you can work really, really hard and get 3 equations, but you need
Need 2 equations.
2 equations. You have 2 unknowns, you have to have 2 equations. Okay, what are they? I don't have the notes memorized, but I can.
The delta G equation.
It's those delta G equations, exactly. And I bet you those delta G equations have wave number and XE in them. Both of them do, right? They both do. So there we go.
But we don't have the plus 3.
Well, how many unknowns do you have?
Oh, just 2.
So you don't even care,
Okay, cool.
right? So I would write down those 2 delta G equations. Maybe I can just copy paste them. Where are they? Here they are, all messed up. Copy those 2, right? And you should be good to go. 2 equations, 2 unknowns. So you have a game plan? Good. Okay. That was 22. 23. Given a plot, gives y-intercept 28, 85.6, and so on. The first 5 vibrational energy levels. Calculate the dissociation energy of the molecule in reciprocal centimeters and, yeah, so let's say electron volts. EV. They want the dissociation energy. What's the mathematical symbol for that? DO. Okay. Well, maybe we can get lucky. Let's start there. What's the equation for DO? Here it is. Where'd it go? That didn't work very good. Where'd it go? That's a lot of work to move. I should just. All right. There. Okay. Why would it give you this? Is this in the book or is this my hint? Oh, we don't have the book. It really doesn't matter. Because this is what I was kind of harping on for some of the pre-labs. Where, hey, where's your plot? Remember when I asked, like Jeffrey, I think I picked on you once. Yeah. Hey, where's your plot? Because what I want you to get used to is when you plot y versus, almost always you plot y versus x. Okay, and here's the game plan for this. What's the equation for a straight line? Well, that's, yeah, that's a straight line, you're right. But what's the general expression for a straight line? Y equals mx plus b. Okay, now what I want you to get used to is this. Whatever goes here is on the left-hand side of the equal sign. Whatever goes here, it doesn't have to be one thing. It can be a bunch of stuff. It goes right here. And whatever's in front of what you plotted, that's your slope. And then you're going to be adding or, well, you're going to be adding. If it's, you can always add a negative sign. But if you're adding, there's your y-intercept. So what we need to do is, it's the delta G versus V. So we find in, that's got to be your equation. Here's your y right here. That's your y. What's going to be your x? The x is going to correspond to the v. So all we got to do is find the equation for delta G, right? Identify, okay, that's the y, that's the x. Well, what's in front of the x? What's in front of the v in that delta G expression? That's going to be your m. And then in this delta G expression, we're adding or subtracting something. Well, whatever you're adding or subtracting, that's your y-intercept. And you know what those numbers are. Okay? So what is our delta G expression? This copy-pasting thing isn't working so good, so there it is. Which one are we going to use? Which one are we going to use? The top one or the bottom one? Yeah, they did. Well, they gave it to you assuming that you're going to figure it out. They said the first 5 vibrational energy levels. So from V equals 0 to V equals 1, V equals 1 to V equals 2, V equals 2 to V equals 3, right? So they figured all those out. I must have plotted them. I don't know why I did that. I could have had you guys plot them, and then you guys get the y-intercept and the slope, right? But I'm pretty sure this is my kind of doing here.
It's on the book.
Yeah, I'm pretty sure this is my doing. I gave you too much, but because I care. Probably because I didn't want to spend all the time making the plot. So the point is let's write down that first delta G expression and see if we can identify stuff here. Show up, show up, show up, show up, show up. Ah, yes. Okay. Now we're see if we can figure stuff out here. My slope is a negative 104.1. So a negative 104.1 is equal to what? Well, you're going to have to do what? You can't use the equation as written. You're going to have to rearrange this thing. So you get a v times something, right? Just rearrange it, see what's in front of the v, and whatever you wrote, all of that will go right here. And I'm pretty sure either you're going to get, what are they after? Calculate the dissociation. We're after DO. So either you're going to get DE or wave number out of that, right? And then the other one, the y-intercept, when you rearrange this, it's going to be plus something. And then whatever you get, that whatever you get there is going to equal, what's the y-intercept? Yeah, 2885.6. So just rearrange this expression. Just rearrange it. It'll work. So we're about out of time. Remember, if you want a pure rotational spectrum, the molecule has to have a permanent dipole moment. So whatever one's permanently polar, and you're done. All righty.